morning.
Hey.
So, such a terrible way to wake up.
Yeah, sorry for being so early.
We'll try to be...
Thanks for coming, anyway.
We'll try to be a little bit more polite. So, what you've seen is actually like a brief summary of the work that we've been doing since the last time we came to KIKK, 10 years ago, 10 years ago. With Playmodes.
We are a research studio. We like to define ourselves as an audiovisual research studio. So we study the relations between audio and visual perceptions. And we've been in the scene for almost 20 years, so we are grown-ups. This time we didn't lose the flight, so we were on time for the festival. We learned something.
Last time they wanted to kill us.
So basically what we're going to do, we're going to explore like 3 projects of the last ones that we've been doing in a bit more depth and trying to let you know how we work and how we do develop our stuff.
Actually, we'll start with Cygnus, and we start with this project because it's actually on display in the Center for International Light Art in Unna, near Dortmund in Germany. It's been exhibited on there for 6 months. It is an algorithmic kinetic canvas made of this light, with these modules. It's a modular installation, so it can take many forms. You're seeing that we arrange them in different matrices, bigger or smaller, and that's because it's based on this module of 1 by 1 meter, which has this kinetic segment, which can rotate, and it can give rise to very different aspects or forms. This is actually the aspect that it has on the current exhibition in Unna, and
you have time until
Sunday,
after tomorrow. So then we are going on Monday to Unna to dismantle. So if you like it, you can hurry up. It's not that far away, but
how many hours in train?
I don't know, but it's Europe here, close.
It's Europe, civilized Europe. It's near.
You get a train and you get in half an hour.
Yeah. So maybe first thing is talking a little bit about how the system works. We are a super maniac of do-it-yourself, so everything that we'll see is done by software tools, hardware tools, systems. It's all built by ourselves, and it's also the case for this installation.
So this is a modular approach that it was somehow when you learn doing installations, you learn that you have to change spaces. So having a modular approach gives us the ability to change location without saying this is too small or too big. And each module is based on this profile or light fixture that you see in front. And this is like made of 3 light sources. One goes to the front, one goes to the up, and one goes to the bottom. The one in front gives you more direct lighting, and the ones up and down gives you more like diffuse lighting, as you see here, which is an aspect of lighting which we want to explore in this work. We are not super high-tech. We are like wood and screws tech. Well, it's not bad, but I mean, there's people much more polite doing this kind of stuff.
But it looks a little bit like secondary school technology.
Yeah, it's like
you wouldn't say this is going to be in a super fancy gallery. It's a little bit...
Basically, what we have here is power supplies for the motor, for the electronics, and for the LEDs. We have a stepper motor, and we have a control electronic board here, and network connection, so each module is connected through Ethernet to the computer, which is ordering the whole installation through sending messages to each one of the modules.
So you've seen it on the introduction that we love creating these visual music instruments. So most of the things that we do explore this very tight relationship between light and sound, and it's also the case for Cygnus. This installation works as a live playable instrument. And actually, we built a rule-based system for it to work. First of all, the installation is algorithmic, or the behaviors are algorithmic. That means that it's quite not deterministic. I mean, the result or the visual and sonic results that you will see on the installation are never going to be repeated exactly the same because it's not timelined. It's based on rules and based on randomness domesticated through probabilities. So this can act somehow as an automate instrument. And what we did was to create a number of rules for the sonification of light, which is more or less depicted here. Basically, each of the modules or each of the segments can have a note associated, like C, like a musical note associated. So when that segment is lit, you will hear that tone. Usually in most of our installations, because we work with large-scale installations, we work with spatialized sound. That means that we have like many speakers, and this is the case for this installation, and we always want that when a specific light is lit on a specific place in space, the sound associated with that light, you are going to hear it coming out from that very same place. So if you see, the segment on top left being lit, you will hear that sound, on the top left as well. And then there are additional rules, like if there are two segments which are aligned, either horizontally, vertically, or diagonally, we're going to trigger a sound and we're going to trigger a specific light pattern. Also, and this is something that we usually do, you see this gradient here with this PPP, FFF. PPP is pianissimo, FFF is fortissimo. At the end, what we want to express with that is that brightness of the light is associated with loudness of the sound. So the darker a light is, the softer its sound is going to be, and the brighter a light is, the louder the sound is going to be. And then the angle of rotation of the segments is going to be related to some property. It can either be like microtonal differences on the tone, or it can be associated with the filter cutoff frequency of the sound, you name it, whatever. It changes from scene to scene, but there's always this very deep will of creating a very tight relationship between light and sound. The installation that we have in Una encompasses three different behaviors, let's say, or three different scenes. On the first one, we play with this idea of algorithmic graphic composition. So what you're going to see now is a little clip of it, and you will see that the segments randomly rotate, but they always stop quantized to 45 degrees. That means that they can just be horizontal or vertical or diagonal. And when there's some alignment of segments, let's say some of them are horizontal, they are going to be lit with a stroboscope, they are going to be lit in white. And all this is going to give some sonic results accordingly. So you can think of it as an automatic graphic design machine, no? And these compositions are never repeated exactly the same again, because there's lots of randomness in it.
The second scene that we have, it's basically is the relation between two entities here represented somehow like the cold white and warm white one. They are in symmetry, and they are like related with the symmetry, and they are moving in composite. And the idea here is that there are many rules related if they are close one to each other, if they are close to the center, and there are like a lot of the variables on how do they react one to each other, which makes that this random, at the end it's a random path, but it's ever changing, and depending on when they are like results like triggering in one way or the other. In this case, the angle of the LED modules is related with each one has a relation where the angle is like perpendicular or pointing at the point of the entity, and the other one is the opposite. So they combine the angles as the light also. When they get very close, they get excited and more energetic relation, and when they separate, they tend to be more relaxed. It's like a living machine, and it's always surprisingly changing effects. Or relations.
So you will see in most of the projects that we're going to show in the presentation that we deal with abstract material. So we're not good figurative narrators, let's say, and we always work with these ideas of form exploration, let's say, or abstract narratives. The third scene on this installation is based on the idea of symmetry patterns. So we created this algorithmic system that creates these symmetric tessellations on the canvas, and also with this idea of inner and outer light. So you see that the light is shifting from the pointing towards the inside or towards the outside, generating this perceivable volumetric effects, so that's something that we wanted very much to do. You also see that when some segments are aligned, you will see it, no, you won't see it. When they are aligned, like now, the front LED strip gets lit and there's a triggered sound. So no, it's all about this kind of no abstract narratives. And again, no, all sound is the product of the angles, the brightness, and the properties of the data controlling the system.
Working with generative systems.
Generative, it's a hijacked word, no? We've been talking a lot about that, so it's a pity that nowadays when you say generative, the idea of generative AI comes into all minds. So the term
it's not the case, so we try to say no, it's algorithmic or procedural, don't say generative.
Yeah.
But yeah, so we're working with algorithmic generation. We usually had a problem, or like, it's easy to create a behavior, but when you want to make a transition between two of these behavioral scenes, it's not that easy, because basically your machine has to run both of these simultaneously, and then you have to be able to make a mix, which is obvious, but usually when you develop a system, say, okay, now it's working, and then now this is working, but we never had the time, or we didn't find a way of how to complement this. In this case, in Una, while we were setting up, because I think we did it just there, that we realized we need to find a way, we made one of the simplest transitions that, let's say, the early video made, which was like a circular gradient, or no, from one to the other, which at the end, it opens a door, and it was not super explored, just in this case, we have this circular transition, but it makes a lot of, it makes a lot of sense, and because you can see both, and you can see the relation between one scene and the other. So we are quite eager to keep on exploring the transitions between algorithmic scenes or algorithmic behavior.
So now we have on the center, we have one scene, and coming from the outer edges of the installation, of the canvas, there's slowly entering the other behavior and colonizing slowly.
And basically here we are mixing light and angles for each one of these, so resultingly the sound also is being mixed in a specialized way.
So now you see that the symmetry patterns almost colonized everything. Now there's just these 4 central remainings of the previous scene until everything is fully colonized by the new scene through this circular transition.
Let's go, come on. So next one is Astres, which actually give name to the talk, because when we were firstly invited here, we said, okay, we're going to talk about this project, but we end up not presenting more projects. This is a project we started like 4 years ago. It's a research project, means that there's no money outcome, so we are not an institute that we can pay ourselves for researching. We do it when we can, but then it takes a lot of time. It's about using natural light. Exploring how can we use natural lights for doing our stuff, let's say, because the context of this was in COVID. Then we have like accumulation of crises. There was a COVID, and then was the Ukraine war, and then was the climate change, like always, and then we have the energetic crisis because of the war. So most of our activity was like vanished. We have a lot of cancellations because of the COVID, and then because of the energetic crisis. So we said, what are we doing? Maybe we should. We had time to rethink and think about which direction could we go to try to be a bit more of environmental friendly. Some of the installations that we do are big scale and they waste a lot of energy, so we decided to try to work with natural light somehow. By natural light we mean working with the day, that we will work with the sun, and with the night that we will work with the stars. Studying the stars is probably one of the oldest sciences that humanity has been dealing with. So from the very ancient times, humanity has been trying to understand what was going on with the stars and the universe around us. And somehow this is like, we are continuing this, and we think that this is like a very simple and let's say it's deep inside our genome somehow, looking at the sky and seeing what's going on. Also, stars are related with time. we are understanding that a day is a cycle between sunset and sunrise, or the whole year. This gives a relation with time also makes sense, and we want to explore what's going on here. So first we start with the day and sun star. It's the closest and easiest and biggest star, so we say, okay, if we work with the stars, we start with the sun because it's the closest. But during the day, the world is full of sunlight, so the idea was to say, okay, first, if we wanted to work with the sunlight, we need to bring sunlight into a dark space. So that was the experiment, or the initial experiment that we did was, can we bring sunlight into a dark space? So in order to make that, we built an heliostat. An heliostat is defined as an apparatus with a moving mirror which is capable of following the sun, but redirecting the sunlight in a precise location all the time. So that's what we try to do. We got some help from a research center around the area and some of our custom electronics, firmware, software knowledge. And the idea was to, as the sun is one of the pillars of life, we are here alive because of the precise convenience of the distance of the sun and the warmth and the light that it gives to us. So we tried to say, okay, can we grow some plants out of the sunlight directed from our mirror? So we built this kind of a weird apparatus, which basically has a mirror on the left side where our heliostat was reflecting the light during the whole day. The light impacts on this mirror and then goes through the tunnel into this dark chamber. The tunnel is to avoid that there's residual light getting into the dark chamber. So trying to be to make that this dark chamber has just the light coming from our apparatus, let's say, or heliostat. For this, we make a little software which, based on your location on Earth and the time, you might know where the sun is, so we can tell this apparatus, this moving head or pan tilt system, to follow and redirect the sun. At the end, it worked, amazingly, it worked, and we were able to grow some plants and seeds. They ended up dying, but they were like growing, so it was, the experiment was like half success. We didn't make a salad out of that.
No, but they died because we were not watering them, not because of the sun. So.
Water. Oh, we missed water.
We missed water. We should build.
So, as you can see here, this is the mirror or the apparatus functioning like for it was like 3 months every day working. This was part of an exhibition in Girona's Contemporary Art Center, but as we wanted to build this on the art center, but it was not easy to make this kind of pipe going to the exhibition center, so we made it on the garden of our studio, and what we did was like a live streaming of the whole experiment, like trying to make grow plants in darkness during the 3 months. This gives us a lot of knowledge on a lot of astronomical aspects, so we were brave enough to say, okay, now that we control the sun, let's go to the stars, or to the universe. The dream was to be able to make a performance in a natural space with light and sound and the stars. It's such a romantic thing that, as we come from the mapping scene also, it was like, okay, the ultimate mapping that we can do is once we control the buildings, why not we try to map the stars? So what we did, we get a van and we go to the mountains close to our studio, and we just point a laser into the sky and say, is it visible? Does it make sense that we work like this? And in fact it was, so we didn't have like a very powerful laser, and it was, the results were like good enough to say, yes, I think we can continue. In fact, one of the goals or the challenges was can we draw on the sky with a laser? And this is a picture of the first day where actually we were drawing in the sky and we were like fucking amazed. I say, how is it possible? Why this is happening? In this case, what we were doing was manually moving the dots or the rays of the laser to match the stars and make pictures out of that. It was the beginning of the process. But we said, okay, if that works, then we need to be able to follow the stars. But that was like a bit complex or too complex for us. So we go to the academia, we relate with the Polytechnic University of Catalonia in Barcelona, and tell them, can you help us to make this? So they told us a bit about, okay, if you want to locate a star in the firmament, there's like a basic coordinate system, a way of finding this, which is called the astronomical coordinate system, which basically with 2 values, which is like from north, how many angles you have to turn, and from the horizon, how many angles you have to go to say, okay, that star is there. There are, so we are in 2024, we don't need to go with like telescopes like hardware. There's a lot of what they call like star catalogs. We have like thousands and millions and trillions of entries, and for each one of the stars that humankind has been able to discover. And with these numbers here, you are able to say, okay, you'll be able to find a star on space, no? From Earth. Basically, for that, you need to know where you are on Earth, no? Exact position on Earth, what's the time, and have a star catalog. And with this, you can know more or less the azimuth and elevation of any star. But then you have to make a software that makes all like a laser scanner point and map this. So what happened is that there were like a group of students working on this challenge. Can we map the stars? With the teachers, and they were like experimenting and trying different ways. And finally, they succeed, and they develop like a simple way of calibrating the laser. Calibrating would be something like finalize or match the mapping, so the laser scanner can know where every star was on the firmament. Calibrating is something like a triangulation. We need to know 3 stars and say, okay, if that star now in my laser scanner at that time from here is here, and that star from now is here and then is here, then the magic of the algebraic calculations make a transformation matrix that allow us to say, okay, everything that is inside of the field of view of the laser is mapped. This is more or less a result or a test of a matching. This is around 3 hours, and you can see we are following the Ursa Major constellation here, and the accuracy of the system just made with triangulations, it's quite amazing. We'll say, okay, next step, we can continue to build something. To build something, generative, algorithmic, procedural, whatever, computer-based system in a ever-changing canvas means if you want to work with a mapping where the building is moving all the time, it's like, what the fuck, no? That was quite a huge challenge. But at the end, it was deterministic because we know with the catalog, we know where all these stars should be. So what we did in our custom framework, we add like all the needed information to read the catalog and get the position of our laser scanner inside the sky view of the place and build something on top of that. Again, now you have, as this collection of stars is going to be changing and every time different, we need to find an algorithmic approach of creating constellations. So we find out that if you make a Delaunay graph, which is this orange graph that you see here, this is a graph which connects all the stars that we have selected, and if there are no crossings. That's a first thing that you can say, okay, it resembles like a constellation. From that, we go to the other one, the one below, which is the blue one. This is another algorithm on top of Delaunay, which makes a Euclidean minimum spanning tree. This means that this tree, or this drawing, contains all the vertices, no crossings, and it's the minimum distance. At the end, it was just looking into mathematics. What are the ways that we can tell the system to draw something that resembles a constellation? So, because we are not sure that we're going to catch a constellation. So we want to explore that, what if we invent or create our own constellations? This is the simulation system. We have a simulation system to work and understand how things are working, which allow us to work in the studio and not always on the field. And these are somehow kind of the results of the first test of creating like algorithmic or generative constellations. As you have seen from the points that you have, you build a constellation. If you restrict which points that you want to work, you can modulate more or less the shape of the constellation. In this case, we are saying, okay, we're just going to use one region of our field of view. This means that we will end up constructing a constellation which it's like a linear structure, no? Because it's based on just in a region. In this case, we are just working with the region of the sky and just turning it. And this creates this kind of changing linear constellation.
At this point, I would say I'm a little bit worried because there's like a difference between the time on the monitor and the time that we have on the presentation. It looks like Marie with her presentation has stolen 6 minutes that we're gonna reclaim.
I think that's a good one.
That's the good 14. One. 14 minutes
that's
50, not 9 minutes 25. Come on, fuck you.
I don't know. What time is it? I don't know. Well, anyway.
So anyway, you've seen on the examples that again we're treating the this installation as an instrument as well. So every time that you see a star lit, you see that there's an associated sound. Every time that there's a new constellation, you have like a new chord, let's say. So again, we built a rule-based system for the sonification of the stars. Following this romantic idea of the symphony of the cosmos or the music of the spheres, and this can be traced back to the quadrivium or Pythagoras or all these ideas about joining together geometry, arithmetics, music, and so on. So the basic rules are each star will have a random pitch associated. This random pitch will be selected from a predefined scale, like a pentatonic scale, expanded through as many octaves as we like. And this might give results like this one. You will see it at the end of this sequence.
Which in fact, this is the beginning of the show.
Yeah.
That we are like starting and we are exploring, from one star we're exploring the neighbors, and then we more or less go on with the performance like this at the beginning.
So we lit a star, we play a note, So the sky as an instrument. We do the same with segments, so it cannot be just restricted to points, but it also can work with segments. And again, this is a generative system or algorithmic system. Algorithmic. So it's unpredictable. So the musical results are never going to be repeated again. Also because the portion of the sky that we're pointing at, the geolocation where we're at, the time at the night and the time of the year is different. So that means that the sky is going to be completely different. So we have that need for a procedural or generative system or algorithmic system. So again, like the brightness of the dots or the brightness of the lines is going to be related to the loudness of its associated sound. Also, in this case, the length of the lines joining the dots is going to affect the volume or the loudness. Usually, we finish the shows with a known constellation. This is Hercules, and we paint it, like slowly paint it and erase it.
Yeah, this is just like a fast forward because we're running out of time.
No, we have 11 minutes.
Okay.
And we finish this. At the end, what we propose to the audience is an immersive experience where we lay out this surround sound system. It's a 20 meters diameter circle, surrounded by speakers. The people is sitting or laying down in the middle. We usually do this in natural spaces where there's good visibility of the stars, and we have the laser in the center, pointing towards the sky. Because we are doing this on natural spaces and because we are somehow controlled or conditioned by atmospheric conditions on that night, we find very interesting things, like on these photographies. This was done during the Aurora Borealis events that happened last May. It wasn't planned or it wasn't expected, and that's why you see this reddish sky. It's not light pollution, it's actually the Aurora Borealis. So it was a cosmical night.
Absolutely unexpected. Mm-hmm. And in fact, we didn't see it live. We see it on the pictures that say why everything is black.
Yeah, we didn't know what was happening actually.
So as we are also in a natural environment, and that was one of the goals of the research, we are working with solar power battery pack. So the whole show could be run from this, and it allows us to also install or deploy all the machines and everything everywhere or anywhere without having a plug, let's say. We can go deep inside the mountains. Many people ask, how is it that the ray of the laser, it's kind of like stopping abruptly? So maybe if you think that pointing a laser into the sky, that you see fading out as it goes up until wherever it goes. So we asked the university, and what they told us that the visibility of the laser, it happens because it's impacting particles in the atmosphere in a certain layer of the atmosphere, which is called the mixing layer, which is around 500 to 1,500 meters, depending. This is variating depending on many factors. It's a climate thing. And this, the laser, when it crosses this area or this layer, there's a huge drop on density of the air. That's why there's an abrupt change on the visibility of the laser. And what we are seeing here on the picture is that when the laser crosses this layer, it disappears visually. As we were saying, every time we go there, we cannot control the clouds still. So sometimes there are no stars, but then you have clouds. And somehow we realized that, at the beginning we say, oh fuck, there's clouds. But then when you see the results with clouds, you are actually painting the clouds, so it becomes even more graphical and you can see the lines. So it's still very nice and very amazing. So you have to imagine that this creates like a 3D structure of around 500 meters long. And the point of view of yourself looking at this, it changes. So the parallax is huge. So you move a little bit and trying to understand the geometries, the 3D geometries is quite interesting in terms of like exploring the results.
I think now we're going to enter the amphetamine mode.
Yes.
Because we're 8 minutes away. KIKK graciously updated our countdown.
Extra.
Thank you for that. So we're going to talk about our last project. It's called Forms. It's actually a wide research project which encompasses different formats. The overall research is about image sonification, again, because we're a lot dealing with that idea of visual music. And the first project is called the sonograph. Sonograph. The sonograph is an instrument thought for primary school students to learn music. It's a commission from the government, or from the Valencian government, from the regional government, which they asked us to create something for children to learn music in an intuitive way. And what we came up with was this instrument which has a camera, and the children can draw their own drawings, put them on the box, press a button, capture that automatically capture that drawing and transform it into sound. So the children can draw their own graphic scores somehow. This is based on a technique called raster scanning. You will see that raster scanning is it's a common thread in all the Forms projects, and here you will have a very easy to understand sneak peek on it. So basically, the children make their drawing.
These are not children.
No, these are not children, and this is not normal velocity. It had to be super intuitive, super easy to understand. So basically, there's this header traversing the image. This header is analyzing the luminance of pixels it traverses and transforming the luminance of pixels into loudness for an additive sound synthesizer, transforming image into sound through raster scanning. This is a publicly funded project. That means that it's been the government, all of the Valencians have been paying for this project. It made sense that this became an open source project. It's in the public domain. If you go into the Playmodes GitHub repository, you can download everything necessary to build your own sonograph at home. It's actually happening. There's many people around the world, or there's some people around the world, not many, hundreds of people, well, come on. There's some people around the world building their own sonograph. You will find the materials list, the source code, the assembly instructions, and so on. A further refinement of this image sonification idea, based on raster scanning, is related to the idea of algorithmic or procedurally generated spectrograms. But maybe first we need to clarify what is a spectrogram. So basically a spectrogram usually is a visual representation of pre-existing sound, of a recorded sound, of the Beatles, for example. And you will see that on the x-axis there's time, so you traverse from past to future, let's say, horizontally, and on the vertical axis there's frequency, so lower frequencies are on the bottom and higher frequencies are on the higher part of the image. And the synced result is something like this. where you can see the contours of the percussion, the contours of the, of the clarinet, and so on. So the idea was, how the fuck can we create images that sound good when they are sonified? And this, you can imagine it with a sonograph. How could I draw something with a pencil that is transformed into a cool drum and bass rhythm, or into a cool symphonic orchestra sound, let's say? So the answer to that is that if we follow very carefully this underlying grid on a spectrogram, the horizontal time grid and the vertical frequency grid, Fourier says, these mathematical theories say that you can virtually create any timbre or any sound. We developed a number of softwares in processing and open framework, Super Collider, to be able to create these random spectrograms and to sonify them in real time. And this is one of the results of that, of that development. So remember, what you're hearing is the product of the image. It's not that we created some music in Ableton Live and then we created some graphics for it. No. It's the opposite. We first created the image and we transformed this image into sound through raster scanning analysis. This technique has given rise to a number of different formats. One is a screen triptych, video projection in different contexts and formats. This was in Sonar Istanbul some months ago. It was a semi-live performance. And what we have on display right now in Amsterdam at Next Museum is the last iteration, which is in an immersive projection form, where people can stand in the middle of the projection. We can see a little snippet of it. So remember, all is product of image sonification. The image is the source of everything. The last iteration of all these ideas was, but can we create a score or an algorithmic score that is readable by human interpreters, by a string quartet, for example? And what we did was to translate all these ideas into a symbolic context. Instead of using gradients, we were starting to use these vectorial graphics based on symbols that humans could read and know that if they see a circle, they need to play a pizzicato, let's say. We built a number of software tools that were creating random graphic scores, like the ones you're seeing. We handpicked the results among thousands of files, and we created a long composition, 20 minutes concert, that we edited in a scrolling image, and we added that together with the electronic sound layer. So here you see the warm colors represent what the string players are going to play, and the white layer on the back is the electronic sound. At the end, the musicians, on a concert situation or on a rehearsal situation, they are watching a TV, like playing a video game with these scores going forward, and they need to transform that images into sound when they arrive to this vertical white line. We can see a small snippet of that. We ran out of time. Thank you, KIKK, for being so... Thank you very much.